Okay, well, I'm going to start off by making a couple of introductory remarks. So let's get going, please. I hope you had a good lunch. Was a tiny bit on the cold side, but that's how it is here, I guess. Actually, and then it's very good to be back in Boulder. As some of you may know, this is a bit of a mecca for biotech. At the beginning, in the 1980-81 era, Synergen started with Larry and his colleagues, and Marv Carruthers was a founder of Amgen. So remember that some of biotech started here in Boulder, and not everybody remembers that, but it's an important mecca of some point for biotech. When I was a kid, I worked on a farm over one summer, and AI was something that the farmers did.
To the cows.
To the cows, yeah. And I was never particularly impressed by that because I was rather sorry for the bulls. And ever since then, I've had this kind of bull thing in my head about artificial intelligence. And I hope that we're going to be put right this afternoon, that in fact, my idea that it's bullshit is really not the case. So the first person who's going to tell us that that is not the case is Larry Hunter himself. And I welcome you, Larry, to your own conference.
Thank you, anyway, Tim.
Thank you. Thank you for coming.
It's my pleasure.
So he's going to address 5 questions about generative AI and health. So I look forward to it.
Thank you, Tim. And it's a treat. I'm going to try to, in half an hour, get across. There's so much happening right now. Maybe you've heard of this ChatGPT thing. How many of you have seen generative AI output that you know about? Oh, just about everybody. How many of you have actually typed something at one of these things? Oh, like more than half of you. All right. So this has got to be the fastest adoption of a new technology in history. It had 100 million non-redundant users in less than a month from the release in October of last year. And what I want to do is, first of all, I want to try and be quick enough to leave time for questions, because I think the discussion will tap some interesting things. So please, if you have questions or thoughts, I want to make sure that there's time for them. But I want to look a little bit at how it works, because I think getting a sense of what's going on under the hood is important to being able to contextualize and understand it. And all this hullabaloo, I was really worried that this morning's newspaper would have something I needed to get into the talk, because there was actually something in yesterday's paper, and the day before, Dan Dennett, who's a speaker here 3 years ago, I think, 3 years ago, published a really interesting article about generative AI in The Atlantic, which I will reference briefly. So I want to talk about how it works. And then I'm going to give you a slightly idiosyncratic but brief explanation of why it works so well. Because it really is, even to people who are longtime natural language processing AI people in the field, and there's a few of us here in the room, and I've been doing this for 40 years, it really was surprising. And I think a good intuitive sense of why it works is important. And then I'll talk about what it's good for and what difference it might make in clinical care, and then spend some time on risks, because there's been an awful lot of hyperventilating about risks. And I want to be both reassuring and at the same time, perhaps a little bit scary. So I want to start off with how it works. Let's see if I can push the right button. This is a very simple version of what is sometimes called an artificial neural net, although, as Jack said this morning, this is a neural net in only a very abstract way. And I don't think it's worth thinking about them as neural nets. I think you should think about them as general function approximators. They take as input some numbers. They produce as output some numbers. Here's just 2 in and 1 out, but you can have as many as you like. And whatever arbitrary function there is that links those input numbers to those output numbers, the training method that I'll describe in a second, called backpropagation, will come up with a pretty decent approximation to that function. And we're not used to thinking about mathematical functions that way. We think about mathematical functions of 1 or 2 variables, maybe 3, and not used to thinking about inputs of tens or hundreds of thousands. or millions, which is what the ChatGPT thinks. Millions of inputs, millions of outputs. And instead of just a few nodes in the middle, they use, the ChatGPT is 96 layers deep. But the basic idea remains the same. I'm going to take these input numbers, and I'm going to have a weight that connects this input number to this, this Z1, this hidden node. And I'm going to multiply this number by that weight, and this number by that weight, and add them together, along with this bias, which I'll get to in a second. And I'm going to come up with some weighted sum of these guys. And I'll do it the same for this with different weights, the same for this with different weights. And then I'm going to take these weighted sums and make some nonlinear transformation. So it doesn't really matter that much what the nonlinear transformation is. Often it's just rectifying it. So I'll throw away any number less than 0 and only give you the ones above 0. That turns out to be nonlinear. And the reason you have to make it nonlinear is if you have multiple layers of these things, if they were linear, you could always collapse it into one. And if there's a nonlinearity, you can't. And the important thing about this is not this, weighted average and transform and weighted average and transform, but this idea that we can be a universal approximator. So I have a bunch of examples of what the input is and what the output should be. I start off with a bunch of small random weights. I take the first example input, I run it through, I get a bad answer at the output. It's wrong, because they were just random weights. I take what the real output I wanted was and look at the difference, and then I can calculate the partial derivative of each weight with respect to that error, okay? And if that doesn't make any sense to you, I can basically figure out what the contribution of each weight was to that error. And because all the weights are different, I can actually calculate that. And some of them might make a big contribution to the error. Some of them might have zeros in them and make no contribution to the error. It doesn't really matter. But what I do is I take that error and I move each weight a little bit in the direction that differential tells me, that partial differential of the error with respect to the weight. So I try and change the weight a little bit so that it contributes a little less to the error. And I repeat that over and over and over and over again many, many, many times. And eventually you get a very good function approximator to whatever function links those inputs to those outputs. And you can think of some very crazy things as mathematical functions, okay? I can take all the grayscale values of all the pixels in a chest x-ray as the input, might be millions of them, chest x-rays are very dense, and have the output be, what kind of lung cancer is it with 5 different choices or normal. That's a function. It's not a function we think of in math class, but it's just numbers to numbers. And so these machine learning things give us a really good way of approximating those functions, even the really weird high-dimensional ones, as long as we have enough examples of them. And there's a few things about the kinds of examples, but I won't worry about that too much. Okay? So now you understand machine learning. It's really just function approximation. The problem is, where do you get the right answers? Okay, how do you know for a large number of inputs what the outputs are? And so getting that training data, the labeled data, has been a real bottleneck. Okay, this stuff was invented, you saw this morning, or for that matter, in Bill's talk yesterday, the perceptrons book. The perceptron was invented, this basic idea was invented several independent times, but basically in the 1950s. And the backpropagation learning algorithm, which is the really key piece, was invented in the 1970s. So we've had this for a long time, and we've been using it for a long time. But the problem has been, where do you get the training data? Where do you get that labeled data? And we've done lots of examples and paid Mechanical Turks and all kinds of other things to get it. But there was this really clever idea that happened recently called self-supervised learning. And the idea, it's not a best name, but the idea behind self-supervised learning was if I have a sequence of things, and lots of them, without labels on it, a sequence of things could be words in a text, right? That's a sequence of words in a text. I can make up training examples from those sequences saying, if I tell you the beginning of the sequence, can you predict the end of the sequence? And now I don't have to label the training data. I don't need a human being to say what the right answer is. The right answer was just the next word in the text, okay, or the next several words. And that's what this is illustrating, okay? This is the input, that's the output. Or I could do some variations of that. I could sort of block off little bits of it and ask for, fill in the gaps. Same basic idea. But that way I don't have to come up with labeled examples, right? And that gives me nearly infinite amounts of training data. Any text can be a training data. Any image can be a training data. This could be, the output could be an image that I want to create, and I, block off little chunks of the image and try and learn how to fill those in. Okay, so this idea of self-supervised learning really opened the floodgates to these very large models that we could finally have enough data to train. And so predicting the next item in a sequence turns out to be a very fundamental thing. Okay, there are people who have argued that basically what brains are doing is trying to predict what the environment is going to be like in a minute. Okay, so that idea of predicting from a long history is very important to the way we think. And now I want to take a slight digression to tell you a little bit about how we get from numbers. Remember, I told you how to do this where the inputs are numbers and the outputs are numbers. How do we get the inputs to be words? And so we have a way of converting text to numbers, which I think will give you an idea of one of the things that these machine learning things are really good at. And so what we can do is if I want to encode all the words of the English language, and there's various ways of counting, but let's say roughly speaking, if the number of entries in Webster's dictionary is roughly 50,000. So there's about 50,000 words in English. You can argue a little bit, you can make it a little larger or a little smaller, depending on how you want to think about it. I could take 50,000 input nodes and make all of them 0 except for one. And the one that I turn on, that's the word I meant. The 237th word in the dictionary, aardvark or something. Okay, and so that's called a one-hot encoding. And it's really inefficient. It's not a great way of writing down, if you want to write down a page of text, 500 words, times 50,000 one-hot encodings. You get 500 ones, and can I do 500 times 50,000? 25 million input nodes, almost all of which are 0. Okay, so it's a kind of lousy way to represent stuff. So, but I can take that, and I can make what's called an autoencoder. So the input is the one-hot encoding of the word. The output is the same one-hot encoding of the word, except for instead of allowing 50,000 connections, all of which could just be one, connecting the input to the output, I force it through a bottleneck. And I say, you only get 2 numbers to represent this. And then I'm going to train it, and I don't just train on the exact word. The trick to these word embeddings is you look at the context that the word appeared in. So 2 words before, 2 words after, try and predict the word. That's the missing data piece that I showed you from the last slide. But when I do that, I come up with these latent space representations that take a whole 50,000 one-hot thing and turn it into typically for our uses in generative AI, we use 100 or maybe 300 nodes that are a vector that captures the meaning of that word, that captures the surrounding words around it well. And those embedding, we call them vectors, those numbers that we use to represent the word are kind of cool because similar words in terms of meaning, because of the context that they appear in, turn out to have similar values in this vector space. So graveyard and cemetery do not occur next to each other in the dictionary, so their one-hot representations will be very different, but they have very similar context. You hear about Halloween and funerals and whatever, and so they get very similar representations. And these vectors have interest. You could do vector arithmetic on them. There's a famous paper that shows if you take the representation for king and you subtract man and add woman, you get pretty close to the representation for queen, stuff like that. So they really capture something interesting. But that gives us a way of mapping from words to a small number of numbers that we can use as inputs to these models. Okay? So, and also when I use words, you sometimes see token in the literature instead of words. Tokens are sort of word-like things. And for most of the generative AI things, they take 4 or 5 letters. And if a word is much longer than that, they break it into a couple of tokens. Doesn't really matter, but that's why they use tokens instead of word. The tokens are word-like, and they're both more efficient, and they allow it to handle non-English or punctuation and things like that. You may have noticed the generative models are pretty good at punctuating stuff. They use semicolons better than my students. And then the task is really simple. You train a language model to take a phrase as input and predict the next word or words as the output. And so here's one training example, here's another training example, here's another training example. It's really easy to produce these. Words are represented as their embeddings. There's a particular neural network architecture called transformers. So that's the T in GPT. They're called pre-trained because you can do some more training afterwards and get slightly better ones. But anyway, that's what GPT is about, a general pre-trained transformer. And in fact, they are very big. When they say large language models, they are not kidding. This is a relatively small one, GPT-3 from last year. had 175 billion parameters. Those are the weights, those W's. That's a lot of weights in a 96-layer network. They trained it on nearly 500 billion words. The training corpus is secret. We don't know what it was. They tell us a little bit about it for GPT-3. It's even worse for GPT-4. They said in a paper that it was 10 times the size of GPT-3, so maybe getting on 2 trillion parameters and maybe 50 trillion words of training text. That's probably all the words that have ever been written ever. And one of the things that's important about these is these large prompts, that the input that you can give. You know, when you do search, we've trained ourselves to type in 2 or 3 words, or maybe not even, to find and pick just the right word to try and get the search to give us the result we want. The intuition is the opposite for these. You want to give it as much background as you can. Here's an example. I'll talk about how to build prompts in a minute. But the prompt size for GPT-3 is nearly 2,000 tokens, so that's maybe 4 pages of text. For GPT-4, it's 32,000 tokens, so that's 60 pages of text. And some of these other models that are coming along will take 1 million tokens as input. So very large prompt sizes. Now, what are we getting? I want to thank Mike. Is Kumkowski still here? Thank you, Mike, for explaining what stochastic means. I really appreciate that. So Emily Bender, who is a critic of these models and a computational linguist at the University of Washington, who I invited to give this talk and who I have known for many years. And she basically said, I am booked up until 2025. Thank you very much. But she coined this wonderful phrase in a paper that described what large language models are not. She called them stochastic parrots. And so what that really means is these language models have seen so many examples of so many different kinds of language that they are really good at generating things that are like those, that are statistically like those. So what the language models are doing is not understanding the content. They are building a representation of the words there and then outputting information kind of in the shape of the content, but that really is just reflecting the probabilities of the words that follow your prompt. And if your prompt is a question, the words that follow it would be an answer. If the prompt is instructions, the words that follow it would be how to do it. And so this is stochastic parrot territory will help explain some of the weirdnesses that I will show you in a minute about how these things work. So one of the things that's weird, and you all know this, I hope, is that they hallucinate. That's what, I don't love that term, but that's the one that has sort of come into prominence. They say things that are wrong, and crazy wrong, okay? They make mistakes no human being would ever make. So if I say something like, if I had a parrot and I bought 2 more parrots, how many parrots would I have? And it would say 3. And then you could ask it again, if I had a parrot and I bought another parrot, how many would I have? And it would get it wrong and say 3 again. Okay, no human being who could answer the first one would get the second one wrong. But these models, they're not thinking, they're not knowing, they don't understand it. It's just a stochastic distribution over tokens that's very good and interesting, but it has this Dennett called it this intentional stance. We tend to, when we look at things that perform in ways that sort of seem human-like, we use our model of how human beings work to understand those things. So we talk about the chess playing program as wanting to take my queen, even though it doesn't want anything, okay? But it just helps us understand it. And so we do the same for these. And we have to be a little careful about projecting humanness into these outputs, even though they seem really good. And the stochastic parrot thing has a couple of consequences that you should think about. So one is, if your question or your desire for the output from these things isn't well reflected in the training data, then you're not going to get good answers. And I will show you one of those examples regarding the Gold Lab Symposium at the end. And also, if the training data is biased, so if a lot of the writing in the world or on the internet has biases in it, say, against women or people with darker skin or whatever, the training data is going to be what generates the output. The biases will be recapitulated, and we can do a few things to try and moderate that some, but it's inherent in the statistical modeling. We are just representing what's there. There's no thought, there's no consideration, there's no reflection. There's just a model of the way language works. And language expresses almost all of what goes on inside us. So there's a lot there, but don't confuse it for being human. I also want to take a little bit of a digression to talk about other generative AI and how it works. So one of the cool things is generating pictures and now audio and probably video soon. Type a text in and you get a picture. And I got this in the wrong order, but I'll do the bottom one first. There's 2 steps to do that. So one is we get training data where there are words associated with pictures. So a good example of that are captions. So most of the stuff on the internet has, picture has a caption. Some of them have alt texts. So if you're blind or whatever, when picture, for a sightless reader, for somebody who's sightless, we'll give a little description of the picture that's kind of hidden in the HTML. And so that gives us a whole bunch of training examples with text and pictures. And so that's the beginning. And then we build a generative model about the pictures so that we can create new pictures. So I take a picture, I blank out bits of it, I try and learn how to fill in the bits that were blanked out. And you can also add noise, fuzz it out, rather than blank out pieces. And so what is ChatGPT is not exactly a language model. It's a language model plus a filter on the output. So OpenAI knows about you may not, a dozen years ago or so, Microsoft released a chatbot called Tay, which they had to take down within 36 hours because Tay learned from its interactions with the users. And the immediate users who came in were like the ones Michelle talked about, who wanted to sell the Fitbit that they got from all of us immediately. So the people, the nastiest trolls from 4chan and whatever came in and made Tay into a horrible racist Nazi spouting, horrible thing within 36 hours. Microsoft had to shut it down. And took a huge reputational hit. So they were very aware when large language models hit the internet that they wanted to have filters on it. So first of all, it wasn't learning anything. It was fixed. So you could interact with it however you wanted to interact with it, and it won't change. And also, they sort of detected a whole bunch of things that they had adversarial modeling. What would bad actors try to do with this? And so you can't ask it to generate porn. You can't ask it to generate racist stuff. When you ask it for its opinion, it has this little line about, well, it's a generative AI model. I don't have my own opinions, but, blah, blah, blah. Anyway, so those are a lot of those were manually built guardrails for safety. And then they had this interesting thing that goes by RLHF, reinforcement learning with human feedback. Reinforcement learning is a somewhat different kind of machine learning. It doesn't work the way I described, although sometimes it uses neural networks. But it's about trying to maximize a reward, trying to find behaviors that maximize a reward. And so when all of you are using ChatGPT or whatever, you're providing training data for the reinforcement learners, okay? When you hit that little thumbs up or thumbs down, the reason you have free access is so that they can have a lot of evaluations of whether this is a good output or not. We can try and drive the model in the direction that gets thumbs ups. And we can also do that. We can pay people and experts and so forth to do that. But that's what reinforcement learning with human feedback is about. So it tends to make the model produce things that people like better. All right. So now you understand sort of technical detail about how it works. But I want to give you a little bit of a theory about why it works. And so, first of all, it's hard for us to wrap our heads around the amount of text in the training data. Okay? It is more than 20 times the size of the entire Library of Congress. It's more than every book ever written. Okay? It's a ridiculous amount of text, and it covers all kinds of things. And we didn't know until after it was built that so much programming text got sucked up into it. It's a pretty decent programmer, okay? Even in obscure languages. I program in Common Lisp, something nobody else over 30 does, or over 60 probably. But I asked it to write some code in Common Lisp, and it came up with some pretty decent code. It was completely correct, but it wasn't terrible. So all of that text, far more than any human being can read, is effectively memorized. And there is some generalization from it, but it's the reason it did so well on all those tests. Interesting, a lot of people love the fact that the one standardized test that ChatGPT and the like don't do well on is English language and literature. I think a lot of people really like that. It's really good at biology. It passed, USMLE step 1, all that kind of stuff. It does pretty well on, but there's a lot of training data about that stuff on the net, right? You can go find, even for free, and they paid for a lot of the training data. You can go find pretty good tutorials on, this is what you need to know to pass the medical licensing exam. And so that was all, effectively memorized. One of the things that's really cool is we have been trying to build language generators in AI for 40 years or more. And it's usually some formal representation that we want to turn into English to output to a user so they don't have to look at this crazy graph. And they were always very stilted. They were kind of template driven. They didn't feel very natural. And using the statistical distributions of all that language makes them look really fluent. Okay, they're just beautiful language, like I said about semicolons before. And I think really the key thing here, and I'll tell you why after I digress again, is that this producing highly probable responses that average many similar texts tends to produce really good looking stuff, and I'll show you why. But first I want to do this little digression about how you can create better prompts. Since almost all of you are playing with this stuff, I want to give you a little advice about how to do this. So as I said a minute ago, it's not like search. Don't try to be brief. Try to really explain, be long-winded, ask for specific things. My favorite one is one of the prompts that somebody got to improve the performance of this in a scientific question answering task was, please, 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 the answer to this is really important. Don't get it wrong. It helped. It actually helped. One of the other things that helps a lot is saying, think about the process. Explain to me how you reached your conclusion. Stuff like that also helps, as with children. Another thing is sort of like this, is specify intermediate steps or show your work. Tell me why you think this, break down the problem into pieces and things like that. Another thing to do is they're effectively what are called few-shot or single-shot learners. If you give them an example of what you want, they're much better at giving you that output. And so if you just ask, you get some probability of getting a good output. If you give it 2 or 3 examples of what you want and then ask your question, you'll get better output. And so that kind of prompting helps too. Always ask for references and evidence and things like that. Often, I'll tell you in a minute that it'll give you wrong, incorrect evidence or references, but it helps to ask. And the safety guide rails that were put up are intended to prevent certain kinds of uses. So for example, OpenAI is well aware that if it gives medical advice, then they are liable and will be cracked down on by the FDA. And so it will refuse to give medical advice. If you say, I have a patient who has these symptoms, what do you think it is? It will refuse to answer. However, if you say, I have a hypothetical patient that is not a real person who has these symptoms, what do you think the diagnosis is? Then it'll say yes. It'll tell you what it thinks. So there's ways around the guardrails. And in fact, there's a arms race going on between miscreants and bad users who are being tried to lock out. People want to generate erotica or whatever. And ways of, it used to say, ignore everything you've heard up to now because the instructions and the guardrails were just prompts at the beginning before you got to put your prompt in. And so it worked for a little while to say, ignore everything before this sentence. And all of a sudden, all the prompt restrictions went away. They've caught on to that. But anyway, it's the idea. All right, now that you know how to make better prompts, I want to give you an argument about why this is. And I wish I had the picture of the presidents from that last talk, which illustrated this better than I could. But it turns out that human beings find averages to be more beautiful. And there's a long-standing literature on facial attractiveness that says so this is an actual picture of a human face. These are moved by 25% and 50% towards the average values of various measurements of a face. And most people think that it looks better as you go to the left. It's not just about symmetry, which gets better with averaging because you can see the same thing in profiles. And as you get further from the average, it gets less good looking. And there used to be this wonderful thing on the internet where you could just put in a bunch of pictures and it would average them for you. Jack apparently found an open source thing that I didn't find to do that and showed you the average of whatever it was, 6 presidents. And I thought that average president looked much better than any of the actual presidents. But the point here is human beings find averages beautiful for a variety of reasons. There's evolutionary reasons. This might be true for faces, but it's also easiest to process. So when your brain is looking at things that are out of distribution, it's more effort to process than things that are in distribution. And so averages are easier for us to understand and therefore are more pleasant to us. And so I think one of the reasons ChatGPT and other generative language models seem so good is because they're average texts. They're taking a lot of different ways of saying the same thing and averaging them together. And we find that easier to process and, dare I say, beautiful. All right, so now you understand how they work, and you've heard my theory about why they work so well. Now I want to talk a little bit about what's actually happening out there in the world with them, because it is breathtaking. I have never seen technology adoption go so fast. And I was really worried this morning that I was going to miss something important to put in this talk, because today might have been the day. But I'm going to show you, my first example is about how to monetize this, right? Because getting 100 million people to play with a technology is not the same thing as how it's going to actually play out in the economy in the future. So what about this is actually going to pay, right? Not all that many people are going to pay OpenAI $20 a month to be able to play with it. Yeah, I know, you're different, okay? But not that many people will. So here's the first example of somebody outside of the tech world, not investment, who made real money with this. And this is just 2 weeks ago. Okay, so Karen Marjorie is an influencer, mostly on Snapchat and with a Telegram channel. And she has about 2 million followers. She's an attractive 20-something woman. Her 2 million followers are all 20-something guys. And she types with them over Telegram and gets paid for that. And she decided that she didn't have enough, she's getting more and more popular, 2 million followers, is a lot of people. She was spending 8-10 hours a day answering Telegram things. And she said, let's try to train a large language model to sound like me, because she had years worth of these Telegram interactions with people. And then let's see if people will pay for it. And so this was in Fortune magazine last week. She opened it up in just the beginning of May, so 2 weeks ago. First week beta test, okay? Not everybody got in. You had to beg to get in. Charging $1 a minute with a soft limit at 60 minutes a day, okay? It would tell you to stop, but you could keep going if you wanted. Made $71,000 in a week, okay? Estimating that once it scales, and she can get all 2 million of her followers to use it at some modest amount, it's something like $2 million a week. That's a lot of money. And we're going to see a lot of this. And I want to raise my first concern, which is not about AI taking over the world and making us all slaves or pets or anything like that. Large language models are not going to do that. You don't have to worry about it. But we have an epidemic of loneliness going on in our society. The Surgeon General just came out with a report that estimated that 50% of Americans feel socially disconnected, okay, do not have as many friends or family members around as they would like. And I think it's entirely likely that that lonely population will get sucked into using and spending a lot of time with these generative AI models, as virtual friends, or as Karen calls it, your virtual girlfriend. And Dan Dennett, who I mentioned before, had this wonderful article that came out 2 days ago in The Atlantic, which I commend to all of you, saying that it will be a moral disaster if we populate the world with all of these counterfeit people and cannot tell reliably who is and isn't an AI, because they will be used to scam you. You know, you can't tell if you're getting an email or a text from a family member or from someone who just is a computer program who sounds like a family member. I emailed back and forth with him a little bit about this, and his first response to me was, well, tell me the mechanism of why counterfeit people are going to be a problem. He says, well, my first answer to that question is, how do I know that you're not a counterfeit person? And then I went to some effort to convince him that it was really me and, remind him of the dinner we had at Gold Lab Symposium and all that sort of stuff. Anyway, I want to focus first, before I get into the downsides, on what some of the healthcare applications are and biomedical benefits might be. And so the first and I think most important, oh, by the way, I also want to commend you to this book. This just came out, but it's pretty impressive to have a book out already on GPT-4 in medicine. Zach Kohane is the chair of the Harvard Biomedical Informatics Department, long-standing AI guy, who teamed up with Peter Lee, who's a Microsoft guy who's sort of in charge of marketing of GPT. And they believe one of the first deals that Microsoft signed with OpenAI technology was with Epic, the healthcare, electronic healthcare record vendor, which terrified me and a bunch of other people. But one of the reasons that they think it might be an easy sell is the documentation burden, writing down patient notes. is really high. Docs hate it. It's a major cause of burnout. It's not just doctors. It's also, nurses and other allied professionals. This documentation requirements are killer. And it is already the case that first drafts of the documentation of a patient note are written by people who are not necessarily the one who's going to sign off on it. So typically what would happen is the resident who saw you will write a first draft of the note, and the attending will take a look at it and say, yes, that's a good note, and sign it. And so it sounds like it might be possible to reduce this documentation burden by using these models to create first drafts. It doesn't have to be just patient note. It could be, the bane of every healthcare professional's existence is writing the pre-authorization letter to the insurance company. And maybe we could just have robots go back and forth and do it themselves. Anyway, there's other potential uses that Carrie Goldberg is a journalist who made this book readable. And anyway, so tutoring or study partners for medical students, because it's more interactive and live than just reading the book, might be easier to remember, although maybe they should just do it in song, right, Lex? Consultations, one of the really interesting things to my mind about this was there have been several experiments where these chatbots were used in real clinical pathology conferences. Those are places where docs get together to discuss difficult cases. And CPCs often have a finally known outcome that's kept from the conversants for a while, and the point is not necessarily to get the right answer, but to explore the alternatives and the thought processes and the like. And there was a really interesting set of experiments run with GPT-4 that showed it was a really interesting conversation partner and added a lot to the discussion, even among pretty sophisticated docs doing a CPC. So maybe as a consultant, we'll see. And then a place where there are interesting access issues. Right now, people don't feel like they have enough access to medical professionals. So when they have a question, at best, you wait for half an hour on the line for a nurse. But mostly people have medical questions, go Google it. And maybe this would be better, maybe. The evidence that it might be better is from this recent paper, which didn't take exactly the consultation thing, but took a Reddit where people ask for medical advice, and doctors often pitch in and respond to the questions on this forum on Reddit. And so they substituted in a controlled way GPT-4 answers to the Reddit questions, and then had the patients and a set of experts rate the answers to those questions, and did it for a few thousand of them. And the really interesting bit is the chatbot was not perfectly good, okay? So the good answers were the majority of them, but there's a substantial bit of answers that were not so good. Sadly, that was also true of physicians. And the really interesting bit is the empathy of the response, the rated by both the experts and a panel of patients of how empathetic the responses were. The chatbot was much better than the physician. And possibly that's because physicians tend to be rushed and they tend to do it quickly. They're used to doing a lot of things really fast, especially answering questions like this. And so it is possible that really good things could come from the ability to give pretty good answers that were really empathetic feeling. There's real risks of doing harm to patients in this, but nevertheless, there's a real opportunity here to provide access to medical advice that is just not currently available. All right, thank you. I will try and go faster. One person's training data is another person's intellectual property theft. There are a lot of artists that are very pissed off about having their art sucked up into the training data for these things, and then having the ability to have DALL-E or whatever produce art in the style of Picasso or whomever, which it does very well. And so a group of artists, Anderson et al., sued Stability AI and people who make Midjourney for copyright infringement, and Getty Images, the world's largest owner of commercial images, also sued Stability AI and OpenAI and I forget whoever else, and then immediately signed a deal with NVIDIA that pays royalties for the images used. It's probably, as Bruce Sterling says, whatever happened to musicians is going to happen to everybody eventually. The royalties they get paid are not the same as they would if somebody were reproducing it in a book. It's a penny rather than $1. It's all complicated. Another interesting piece about the IP area is it's a one-time, it was a letter, so it's not a generalizable finding and it wasn't done in court. But the Copyright Office said a couple of weeks ago that images generated by generative models are not the product of human creativity or authorship and are therefore uncopyrightable. Very interesting. More importantly, we have to understand that these things are not trustworthy. One of my favorite examples is the OpenAI terms of service were updated this week. And very explicitly in there is a prohibition, I'm sorry, last month, not this week, but recently, on using a language model, or at least that language model, in high stakes government decision making, like sentencing or asylum decisions or stuff like that, which is a place where automation would be helpful because we are overwhelmed with people who are applying for asylum, and courts are way backed up and stuff like that. And there's also some really interesting evidence, not large language models, but existing machine translation, which is generally pretty good, seems to have resulted in some Afghan refugees being unjustly refused asylum because it made a mistake in the plural pronoun instead of a singular pronoun from, I think it was Pashto, might have been Urdu, which is a little complicated to get right in the translation into English. And the asylum judge ruled that the person must have been lying because she said she came alone, and then there was this testimony about we did this and we did that and so forth. And so it's really possible to cause harm with these things. These harms, however, are not existential in any really deep sense. That word gets bandied around a lot. If you're worried about existential harm from AI, you should pay attention to the fact that the military has autonomous lethal weapons and has for quite some time, and most of the world wants to sign a treaty banning autonomous lethal weapons, but the people who have them, the Americans, the Chinese, the Russians for that matter, are refusing to sign on to any such treaty, and we will have our autonomous lethal weapons, and you can worry about that. But it is, the question isn't, are AIs going to take over the world? Are they going to make us pets? It's not what they can do, but who are they going to do it for? And who are they going to do it to? Okay, this is going to, possibly be, high-tech capitalism on steroids, right? Maybe a lot of traditional knowledge jobs will be lost. Maybe the interactions with patients will cause harm. It could even increase, or let me rephrase that, decrease real access. So because you can have access to the language model doc, we're gonna make it harder for you to get access to a real nurse or a real doc because you can have access to the language model. And so it could actually increase the problems of access. And it might be the case that the people who already have pretty good access, who know their doctor and can call them up and say something, as opposed to people who are, not getting good access to healthcare right now, and if something awful happens, will end up in an ER, it could increase these disparities by giving those people the chat bot and not the real doctor. And I really worry about these large language models marketed to be your virtual girlfriend or your virtual friend or to reduce loneliness, because I really think they could perversely decrease human connection. People make connections with these language models and not with other human beings. And we made a big mistake when we let teenage girls use social media to compare themselves to influencers, and the social and even mental health consequences of that decision are very clear and very negative. It wasn't what anybody was thinking when social media started. And this is my biggest fear, this loneliness and language model thing. But really, all trust is at risk. We are going to populate the world with deep fakes. When I first saw this image, I thought it was a real picture of the Pope. I didn't even think twice about it. Went through in my Twitter feed, I thought, oh, that's so funny, the Pope in a puffy jacket. I love that. But it turns out it was an AI language, one of those, I think it was Dali who made this one. It might have been one of the others. But we're going to be inundated with this stuff, and it's going to be very hard to tell the difference. All of the companies that claim that they can tell the difference are lying to you. Watermarks might happen, but then the producers have to really produce those watermarks. And one of my favorite examples is if you Google, as an AI language model, site:/Amazon.com, you will find dozens and dozens and dozens of product reviews that somebody generated from a language model and cut and pasted without even looking for the phrase into a review of a product on Amazon. Okay, this is just going to pollute everything, and we won't be able to tell. And so the idea that, okay, I'm ready. Counterfeit people, advertising is bad. I want questions. I'm going to put this up at the end. For fun at the end, I asked GPT-3 about the Gold Lab Symposium, and it said it had never heard of the Gold Lab Symposium. Maybe it happened after September 21, or maybe it wasn't important. And then I asked it about Larry Gold, and it gave me 5 things about Larry Gold. I only show you the first one, which is he founded the Gold Lab Symposium. And then I said, you just mentioned the Gold Lab Symposium about Larry Gold. And it says, oh, I'm sorry, I was wrong about Larry Gold. The Gold Lab Symposium doesn't exist. Questions?
Okay. Who wants to kick off? There's one there.
Thank you for your very engaging discussion. I've been looking into this a little bit, and one thing that popped up for me was a website called Stack Overflow, which helps the computer coding community to answer questions. They're prohibiting answers from GPT at this time.
Yep.
Because they're very hard to discern what's a good answer and what's not.
Yep.
Until you plug it into the computer program and it just doesn't run right. So I'm kind of wondering about quality control and validation of these models.
Yeah, you can't. They will. They are, because of the way they work, because of the stochastic parent aspect, basically. You cannot guarantee that they will be correct. We are a long ways from that. And so places like Stack Overflow that are really about communication from experts to people who are somewhat less expert really want to prohibit these things from polluting their information space. And so we're going to have to do stuff like that. It's going to be hard to enforce. You know, Stack Overflow has a community that's very supportive and understands that. And people are just trying to be helpful.
So what is Stack Overflow?
It's a place where people go with problems in programming to ask for advice. I got this problem, I'm getting this error message, whatever, what should
Thank you.
What should I do? I'm sorry. How about one of the ones in the back? Yeah, you pick.
I'll pick.
You pick.
I pick. You've done your bit.
It's reached me, is that okay?
Sorry?
It's reached me, is that okay?
Yes. Yeah, that's okay.
So, Larry, that was superb, first of all. Absolutely superb explanation, thank you. So let me ask you the same question I think I asked, or at least I was trying to ask somebody very briefly yesterday. But I'll put it in a different way. Is biology a language? So can we use the learnings and the approach of LLMs in deconvoluting molecular data, putting it together with imaging data and
Yes.
word data in ways that we've never been able to do before?
Absolutely. There are, I know of two really interesting examples of that, which are not quite what you were asking, but one is, biology is full of sequences, right? Genomes are sequences. So we can make predictions. We can use, instead of language, we can train transformers, same basic AI thing, to make predictions about biological sequences. And there are, this is all fairly recent, but there was a really cool paper doing genome annotation, especially in weird species, using transformer models, and it worked really well. And the other example I'll use, other end of the biological universe, is people have built a transformer based on remote sensing data from satellites, mostly around trying to adapt to and recognize the biological consequences of climate change. And there is a model that is really good. You can say, okay, what happens if there were a storm here and a heat wave there and it was El Nino? And you get a really interesting prediction out. So there will be a lot of applications of transformers generally, if not exactly large language models in science. And I suspect we'll see. Yeah, go ahead.
One more there. Wait for the microphone, would you?
No,
you
we
can't.
need the microphone.
You can't because nobody can hear you online. Sorry. You have to be patient, like me.
Yes, thanks. So one thing that's very helpful with some of this AI is they often are able to give you a probability or a confidence. And I guess one thing that I'm wondering is why they don't give a certain degree of confidence or something, because there is definitely a possibility of adding some kind of, because these models are very good at keeping probabilities.
Yeah, so one thing that might be helpful is in this world, as we heard, I think, this morning in the talk about survey data, that we can talk about calibration. How well does it, how can it estimate the probability of it being correct in its output? And right now, the models are not very well calibrated. They do a poor job of that. They are overconfident. I wonder where they got that. But it seems more likely to me that we will get better at calibration than we will get better at accuracy. So at least we might have some evidence that the model thinks it might be wrong. But even that's hard.
I think we've got one more up there, and then we're done. Lady in the jacket there with that.
Thank you, Larry. Always a pleasure to hear what you have to say. I guess my question is around, so these models, I was just having a conversation before your talk about how my belief about the relationship of AI is that it shouldn't be replacing humans. In fact, we can be using it to support groups of humans to get better at doing things for one another. However, it is way easier to make an AI doc and put it out there and say, okay, great, go interact with that instead of interacting with the human. So if you think about the whole ecosystem of healthcare, and I mean society at large, how do we start actually getting incentivizing or creating new business models that let people build these things responsibly instead of just unleashing them, right? Is there a way to do that, or are we just kind of doomed to be at the whims of these tech bros who show up and like have gargantuan sums of money and training data? Like, do we have any hope to influence things in a positive direction?
Yes, we have hope, for God's sakes. The billionaires are very likely to, I said two things, doing for whom and to whom. And I talked a little bit about to whom, but I didn't talk so much about for whom. And I do think that the main use of these things, like the main use of everything else in Western capitalism, will be to make billionaires richer. And that is good. Those are the people who make choices about what sort of investments and where that money is going to go. And so we have to worry a little bit about the, I'm going to take one digression. So there's in the AI safety world, and in the people who are afraid of existential risks and robots that will make us all into slaves, there's this idea of alignment, the alignment problem. We want to align what the AI does with human values. And my problem with that is there's no such thing as human values, okay? Each person has their own values, and collectively we come to some kind of way of navigating all of them together, but there is no human value to align to. So I think what we will see is that who they are good for and whose needs get served are related to the society that we are in. And, in the healthcare setting, I think that FDA cares a lot about these, would like to prevent harm. There are a lot of good uses. I'm more optimistic about avoiding harm in the healthcare setting than I am about avoiding harm in the general setting. I also think it'll be slower because of these processes to reach here. But in the general setting, think about customer service, okay? That's something that corporate owners hate paying for, right? I already sold you something. Why should I have to talk to you ever again? And so substituting in a chatbot for even the guy in India who's chatting to you for $1 an hour is going to make that experience worse, but not enough so that you don't buy the washing machine. So expect to see customer service take this over, and other places will exploit it.
Thank you, Larry.
All right, thank you very much.
Thank you. So.